is equal to sigma 1 minus sigma 3 divided by 2. And this is basically 100 minus sigma 3. This is minus 20 divided by 2. And this is basically 120 divided by 2. This is 60 kilonewton over meters squared. And sigma n is basically sigma 1 added to sigma 3 divided by 2. And this is equal to 100 plus minus 20 divided by 2. So 100 minus 20, this is 80. 80 divided by 2, this is 40. It's 40 kilonewton per square meters. So this is 60. And this guy here is 40. And I pretty much have everything else in there. So I can put this back into the equation. I probably just write it there. So you have 60 equal to or equal or smaller than 40 tangent of 7 or pi over 7 plus the cohesion 70. Now, if this is larger, then the material is safe. If this is larger, then the material is less safe. So the safety factor is this number divided by this number. So if you divide 40 tangent pi over 7 plus 70 by 16, you get 1.488, and this is the safety factor. As I said, this is the large, I mean, as far as this is large, or as far as this is larger than this one, then the material is safe. Once this side becomes larger, then the material has failed. So the safety factor is the safe side divided by the unsafe side, if you want to put it this way. So a safety factor larger than 1, then this would mean the material is safe. But let us now solve an example. And then you try to do this example yourself. Okay, so the example is slightly different. I want to give you 5 minutes to try to solve this example yourself, and then I'm going to solve it. So again, we have some material. The material is undergoing a uniaxial compression test. So the uniaxial compression test, this would mean that the material here is undergoing the compression, and the compression is happening through one axis. So sigma again is going to be F divided by A, where A is the cross section and F is this force there. And the stress tensor would look like this. So it is going to be sigma 0, 0, 0, 0, 0, and 0, 0, 0. So this is the stress tensor. So I want you now to try and find F, basically, if you know that the material has this type of properties. So, or probably I want you to, so the material properties are given by the cohesion and the internal friction angle, and you need to estimate the maximum force applied on the sample before the material has failed, or before the material would fail. So what would be the maximum amount of force this material can take? You know that the cross-section is given this way, and you know that the internal friction angle and the cohesion are given by that. So I want you to evaluate F, and then I want you to evaluate F again, I mean, considering Mohr-Coulumb criteria, but then I want you to evaluate F again using the Rankine criteria, and given that sigma ultimate is 250 kilonewton. Okay, so I want you to think about the example, read the example, try to solve it. I'm going to give you 5 minutes to think about this, try to use the equations we have been learning so far, and then I'm going to solve it myself. If you are able to solve it, then please write the answer in the chat. Okay, I think you should be able to solve that, but just in case you are not, I'm going to solve it later myself. But if you are able to solve it, if you are able to estimate F, the maximum F, then please just write it in the chat. we have the stress tensor again, exactly like before, the same like before, and this is sigma 1 and 0, 0. We know sigma 1 is basically F divided by A, but for the time being, we're just going to use sigma 1. So tau is going to be sigma 1 minus 0 divided by 2, so it is sigma 1 divided by 2. And if we look into sigma n is going to be exactly the same thing, so it's going to be sigma 1 plus sigma 3 divided by 2, and sigma 3 is 0, so this is equal to sigma n as well. So sigma n is equal to sigma 1 divided by 2, and tau is also sigma 1 divided by 2. So you have sigma u, so you have sigma n, and you have tau. Both of them are available for you. So if you do that, you are going just to substitute into this equation here, and then you have sigma 1 divided by 2 is equal to sigma 1 divided by 2 multiplied with tangent phi added to the cohesion. Now the cohesion is 55 and the internal friction angle is 30. So you just basically replace them. So this is pi divided by 6. I think this, yes, so 30 degrees is pi divided by 6, and the cohesion is 55, and this is sigma 1 divided by 2, and sigma 1 divided by 2. In this equation, the only unknown is sigma 1 divided by 2, or sigma 1 basically. So sigma 1 is on this side and sigma 1 on this side. So you basically take sigma 1 divided by 2 multiplied by tangent of pi over 6 to the left end. You take sigma 1 as a common factor. You divide by tangent, or 1 minus tangent pi over 6, and you multiply with 2, you get this number. Okay, once you have sigma 1, you know that F is going to be sigma 1 multiplied with A. This is equal to F. You just multiply with A, you get F. And the cross section is 0.02 square meters. Be careful here because the cohesion is kilonewton per meter square. So when you get the value of the stress, when you get the value of sigma 1, this is going to be in kilonewton per meter square. And then when you multiply with A, you need to make A in meters. So in meters, this is 0.02 multiplied with the F, so you get 5.2 kilonewton. Now, if you want to consider Rankine criteria is quite easy. Sigma 1 is equal to sigma ultimate. This is the point where you have the failure. Sigma ultimate is given. So the sigma ultimate is 250 kilonewton. So sigma 1 is equal to 250 kilonewton. If sigma 1 is equal to 250 kilonewton, A is 0.02. So you multiply 250 kilonewton with 0.02, you have 5 kilonewton. So according to Rankine, the material is going to fail at 5 kilonewton. And according to Mohr-Coulumb, the material is going to fail at 5.2 kilonewton. Okay? So Rankine is more conservative. Rankine is assuming that the material is going to fail at 5 kilonewton. Mohr-Coulumb is assuming, no, I mean, so if you imagine Rankine is talking, Rankine is going to tell you, well, once you get into 5 kilonewton, your material would fail. Don't push the force beyond 5 kilonewton. If you imagine Mohr-Coulumb talking, then in this case, they would say, well, you can push it up to 5.2. Is not going to fail up to 5.2. So you can get 0.2 more kilonewton loads without failing. So this is why Rankine is more conservative. It's underestimating the force, if you assume, or this is overestimating the force if you want to assume that Rankine is correct. And as a designer, as someone who's going to design, if you are a conservative person, you would go for this number. If you are a less conservative person, you would go for this number. So as a designer, your personality or your personal choices are going to decide on your design eventually. Okay? So up to you as a designer which criteria you want. As long as the criteria is valid or the criterion is valid, is your choice to choose that.